Hello, I'm Dave Brown for Teletrain, and today we continue our study of Parker Hannafin's text on industrial pneumatic technology with Chapter 9, which covers flow control valves, silencers, and quick exhausts. This is a typical flow control valve. It is used in pneumatic circuits to affect actuator speed. Here it is in action. The flow control valve here is slowing the speed of this cylinder by acting as a restriction to partially block flow in the circuit. And as we explained in Lesson 7, the speed of actuation of the pneumatic cylinder is affected by how quickly it can be filled with air at its inlet and exhausted of air at its outlet. There are several different flow control valve designs, but they all operate on the same principle. And to understand how they work, we should explain a new term: orifice. An orifice is a relatively small opening which we place in a fluid's flow path. Here is a simple one: a disc with a hole drilled through it. The size of the opening, or orifice as it's called, affects the flow rate. While other factors, such as the length of the restriction and the pressure on each side of the orifice, will affect the flow rate, the variable most often used to control flow rate is the diameter of the hole, or its cross-sectional area. A good example showing this relationship is a leaky garden hose. The hole in the hose is an orifice. If the hole in the hose is small, as we have here, the flow is limited. It appears as a drip or spray. But if the hole is large, as we've purposely made it here, the leak will be a stream of liquid. So you can see, by varying the diameter or cross-sectional area of an orifice, we can regulate fluid flow. The orifice we have just described is called a fixed orifice because it is not adjustable. And when it is used in a pneumatic circuit, it will provide a fixed and constant flow rate, provided the pressure remains constant. A fixed orifice can be as simple as a pipe plug with a hole drilled in it, like this, or a check valve with a hole drilled through the center. Factory preset flow control valves are also available. And here is the symbol used to represent a fixed flow control valve. For most pneumatic applications, however, the system normally requires a flow control valve with some sort of adjustable orifice, so that flow can be increased or decreased to meet the special needs of the circuit. And there are several types of adjustable flow control valves available. A common adjustable flow control device is a ball valve, like this one. By rotating the ball with this handle, the opening can be varied, which in turn varies the flow. Since a slight movement of the handle makes a large difference in flow, the ball valve isn't widely used for flow control. This globe valve is an adjustable orifice device. The disc or globe can be raised or lowered against a seat that has been machined into the valve body. Since this action changes the cross-sectional area through which the fluid passes, the flow rate can be regulated. Here is a typical needle valve. The orifice size is changed by raising or lowering the cone-shaped tip of the needle in relation to the valve seat. By using fine threads on the valve stem, the orifice size can be changed very gradually, providing more precise flow adjustments. The needle valve is the most common type of flow control valve used in pneumatic systems. Here is the symbol used to represent an adjustable flow control valve in a circuit diagram. Before we go further, we should mention one other important point about using adjustable flow control valves. That is, in most system designs, flow control valves are used to regulate flow in only one direction. So the valve construction often has an internal bypass check valve which offers little resistance to airflow in the reverse or free flow direction. Here is a typical needle valve package. It is often called a sandwich flow control because it's designed to be inserted between a directional control valve and its subplate. This particular unit has two needle valves here and here. The passages which direct airflow to the directional control valve are cast into the valve, as you can see here. And since the unit utilizes two needle valves, it's often a convenient unit to use when a circuit requires a cylinder to have different rates of extension and retraction. One final point before we examine some pneumatic circuits in which flow control valves are used. Most frequently, a flow control valve operates in a circuit by restricting or metering the flow of air out of the cylinder. This type of usage is called meter-out control. In other words, the flow control valve works by developing a back pressure that slows the movement of the cylinder. The closer the flow control valve is mounted to the cylinder, the more accurate the control will be. But if the force on the actuator varies during the stroke, or if extremely stable velocity control is necessary, the use of a hydraulic dash pot may be required. A shock absorber on your automobile is a type of dash pot. And just as it smooths out the bumps in the road, a dash pot in a pneumatic circuit can smooth out the irregularities in a cylinder's motion. Okay, we've examined how a flow control valve works. Now let's put our knowledge to use by looking at several circuits. Here's a basic one. The main system components are this single-acting cylinder here, this three-way directional control valve here, and this variable flow control valve. With the directional control valve in this position, airflow into the cylinder is unrestricted, and the actuator moves in the upward direction. And since there is nothing to restrict the airflow, it will move at an uncontrolled rate. When the valve member is moved to the opposite position, air exhausting from the cylinder must exit through the flow control valve here, and the retraction rate will be controlled. In many applications, however, the system will have a double-acting cylinder, and it may be necessary to control the actuator's speed during both extension and retraction strokes. Here is a circuit in which extension and retraction are being controlled at different speeds. The circuit uses this four-way directional control valve, as we described in Chapter 8. And you can see the two flow control valves here and here, which control the airflow of this actuator. It has a slow extension rate and a relatively fast retraction rate. This is the circuit diagram for the system you've just seen in operation. Here is the four-way directional control valve, here is the cylinder, and here are the two variable flow control valves. When the valve is in the energized position, as shown, the air supply is directed through the open check valve here and onto cylinder port A. The exhausting air is stopped by this check valve here and forced to pass through needle valve 1, which has been preset to provide the proper restriction and give the desired extension speed. When the directional control valve is shifted to this position, the air supply is now connected to port B. Air exhausts through port A of the cylinder, and its flow rate is controlled by the setting of needle valve 2, here. It is this flow valve setting which controls the rate of cylinder retraction. We should point out something important about this circuit that has just been described, and that is during both actuator extension and retraction, the velocity was controlled by the rate at which air was allowed to exhaust from the cylinder. Many times, a 5-ported valve is used for this application, in which case the circuit looks like this. A more detailed explanation will be found on page 107 of your text. Okay, let's examine another circuit in which flow valves are used. It's an application such as we see here, where more than one speed is required as the actuator moves during the extension and retraction strokes. For example, suppose that during the extension stroke, we want the cylinder rod to have a speed of 20 feet per minute for the first 5 inches, and then a rate of 5 feet per minute for the remainder of the stroke. Then on the return stroke, a retraction speed of 25 feet per minute is required. Since 3 speeds are required and the cylinder must change direction, we will need 3 flow controls and a directional control valve. While several circuit designs could be used, here is one that will do the job for us. Let's identify the circuit elements. First, we'll obtain directional control with this 5-ported, 4-way directional control valve here. And we've set these 2 flow control valves, 1 and 3, to provide the fast forward and fast return on the cylinder rod. To obtain the reduced speed in the forward stroke, we will need not only this 3rd flow control valve, Z, but also a means of detecting cylinder position, since the specifications require a drop to 5 feet per minute after 5 inches of travel. To do this, we're going to use this normally open or passing cam-operated valve. When the valve plunger is at rest, as you see here, the valve allows airflow from here through the valve to this port. However, when the plunger is depressed, as shown here, the valve is closed and no air is allowed to pass. This technique allows us to control the airflow based on the position of the cylinder rod. Here is how the valve is represented in the circuit diagram. You can see that it is connected in parallel or across the flow control valve, Z, which has been set to establish the slow forward cylinder rate of 5 feet per minute. Our system also uses a check valve here to permit free flow around the flow control valve when the cylinder is being retracted. Okay, we're ready to look at how the system operates. When the circuit is energized, the spring-loaded directional control valve is positioned so that air is directed to the A port of the cylinder. Some of the air exhausting from port B passes through this needle valve, Z, but most of it passes through the normally open cam valve here, and then exhausts the system through needle valve 1 here. This valve has been set to the proper flow rate to give the desired fast forward cylinder extension speed of 20 feet per minute. The first 5 inches of extension is the fast forward portion of the cycle. Now, take a close look at what happens when the cam on the cylinder shaft activates the cam-operated switch. Notice how after 5 inches in the forward stroke, the speed of the cylinder decreases. When 5 inches of forward stroke is sensed by the cam valve, it shifts to its closed condition. All of the exhausting air is now forced to pass through flow control valve Z here, which has been preset to provide a speed of 5 feet per minute. The cylinder exhaust pressure begins to build up, and the cylinder extension rate is gradually reduced until the new pressure balance and slower speed are reached. At the end of the stroke, the directional control valve is released and the actuator retracts. We can see what happens then using the circuit diagram. You can see that the directional control valve has now shifted and is positioned so that air from the supply is directed to cam valve Y here, which is now closed, needle valve Z here, and the bypass check valve here. Since the bypass check valve has the least resistance, nearly unrestricted air flows into cylinder port B. Air exhausting from port A passes through the directional control valve here and then into flow control valve 3 here, which is set to control cylinder retraction rate at 25 feet per minute. As we said earlier, there are many circuits which could provide the same multiple speed control, but we selected this one since it uses many of the pneumatic components we have covered so far in this course. Before concluding this lesson, we should mention two other special purpose devices which are often used in pneumatic circuits: quick exhaust valves and silencers. Here is a quick exhaust valve. It is most often used with three-way or four-way directional control valves to increase exhaust flow, and its purpose is to speed things up by providing a shortened path for the exhaust to reach the atmosphere. In many pneumatic systems, unmuffled, exhausting air can generate quite a high level of noise. Over long periods of time, this may cause loss of hearing and operator fatigue. So to reduce this noise, the system may be equipped with a silencer, or muffler as they're often called. And there are several types of silencer designs used today. Energy of air exhausting from the system is diffused and the noise is reduced. Some silencers, like this one, are made from porous substances. As the air exhausting from the system diffuses through the small openings, the air energy is absorbed and the noise is reduced. The pores in these units can become clogged, so you should be careful to give them regular maintenance and keep them clean. Here is the symbol used to represent a silencer or muffler on a system schematic diagram. This ends Chapter 9 of Industrial Pneumatic Technology. The review exercises which accompany this lesson begin on page 113 of your text. I'm Dave Brown for Teletrain.